So last time we talked about sequences. So remember that a sequence is just a list of numbers, and we talked about taking the limit of that sequence. Okay. Now, if the limit exists, I can't speak today. If the limit exists, we say that that sequence converges to that number. And I discussed last time how what it means is the limit exists is that at some point in the sequence, every single number after that point is pretty close to what the limit is equal to. It keeps on getting closer and closer and closer and closer and closer and closer to that value. So what we're going to actually do now is take our knowledge of sequences and apply them to series. And I will explain what that is. So actually I should have series here. So you go into the writing mode. Okay, that's not what I wanted to show. There we go. Okay. So what are series? So a series starts with a sequence. So you have your sequence AN. Okay, it's not writing. What's going on? Okay, let me close this and open it again. Why is it not letting me write? What the hell? Okay, technical difficulties? Okay, let's see if it lets me write now. Is it gonna let me write? Shit. I'm like clicking and like nothing's happening. Okay, I can type. Okay, there we go. Oof, I was like, okay, that threw me off. Okay, so you start with a sequence. AN. You have some formula for it. And then here's like, you start at the first term and you go all the way to the last term, all the way up to infinity. So the series of a sequence is just the sum. So you have the sigma. Oh, yeah, thank you. Record. There we go. So the series is just where you add up all of those terms. So notice my index variable is n. So, right, so this is a1 plus a2 plus ... an forever and ever and ever. Okay, so a series is just the sum of the terms of a sequence. So it's the special name that we have for when we add up all of the terms. Okay, and then you should recognize the sigma notation, right? Right, from Riemann sums. That's why we learned about it, because we're going to use this here. And notice your n in this case is your index variable. It needs to match with the variable for the formula for your sequence. All right, so the index variable should match the variable for the explicit formula of the sequence. And then we talked about this before with Riemann sums. The number on the bottom is your lower bound. The number on the top is your upper bound, right? You would add from the first term, infinity means, to the infinite term at the end. Okay. So, this is sort of a problem. We're adding up literally an infinite number of terms. If you add up an infinite number of things, that doesn't really make a lot of sense, right? Because, like, how do you complete that action? Do you get what I mean by that? Like, you literally are unable to add up an infinite number of things, like if you were to like sit down like a bead counter and start counting, basically. So how do we get around this problem? The way that we get around this problem actually is using limits. So how do we get around the problem of adding together an infinite number of terms? Why is it not letting me put a question mark? Okay, if I do 3 dots and then a question mark, it becomes a 4th dot. But if I put a question mark, it goes like that. Okay, whatever. Well, there will be no 3 dots. Okay, so we're going to use limits. Okay, so what you're going to do... So I guess I should give a name to this. Whenever I say a series, I mean literally adding up the infinite number of terms. So if I just say a series, I'm adding up all of the terms. Why am I saying a series is all of the terms? Because there's something called a partial series. A partial series is where you only add up some of the terms. Okay, so usually we use the letter S to denote the series of what everything adds up to. So if I say S stands for series, it's the sum of all of the terms. A partial series, what you do is you write S and then you write a subscript. So SK is a sum of the terms in your sequence where you add the first term and the last term is the kth term. So you get A1 plus A2 plus dot 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 up to AK. So we call this the K partial series. So S underscore K is the K partial series, which is the sum of the first K terms. So as an example, if I say S5, what is that? It means you're summing from n equals 1 to 5 of the terms of your sequence A1 plus A2 plus A3 plus A4 plus A5. Right, so S100 would be the sum of the first 100 terms. S1 million would be the sum of the first 1 million terms. Okay, now here's the interesting thing about this. Let's say that you have Sn. Let's change the color here. Or let's just do Sk. So Sk is the sum of the first k terms. Okay. Sk plus 1 is the sum of the first k plus 1 terms, right? Which means that it's going to include all of Sk, right? So in fact what you get is Sk plus 1 is Sk plus one more term. And what is that one more term? The k plus 1 term, right? Because Sk has A1 all the way up to AK, right? It explodes, it like expands to all of that. And then you need to add the kth plus 1 term. So what this shows you is that, okay, as you, or, sorry, I guess I should say that a partial series contains the sums of all the previous partial series. Right, so like S6 is S5 plus some more stuff. S10 is S5 plus more stuff, right? So what this means is that if all the terms are positive, your partial series is only going to get bigger, right? You're going to keep adding to it. So let's put that. If the terms are all positive, then the partial series are growing. In other words, they're expanding, right? Because you're always adding something more to it. And this is going to be really important to us. So we're going to come up with an example. Okay, so let's say for this example that our sequence AN is 2 times 1/2 to the n minus 1. Okay. And what these numbers mean is, let's say that each day you fill some water into a bucket. The first day you put in 2 gallons of water. The next day you put in 1 gallon of water. The next day you put in a 1/2 gallon of water. And so on. Okay, do you notice how there's like a pattern here? There's a sequence to the amount of water I'm like putting into the bucket. On the first day it's 2, then 1, and then 1/2. Do you see how I'm halving the amount of water that I'm adding each day? That's why it's a geometric sequence, right? Hopefully you can recognize the explicit formula of the geometric sequence. Okay, now the question is, if you repeat this process forever, how much water will you add? Like, if you just keep on doing this forever and ever and ever. Well, actually, interestingly enough, it's not an infinite amount of water. So, but the answer to our question is that to figure out the amount of water that you would add, that is the series, right? We want to figure out what do you get when you add all of those infinite number of days of stuff, right? Okay, and what we can do is we can actually investigate the partial series to see, like, hey, let's look at how much water I've added by the first day, up till the second day, up till the third day, up to the 10th day, up to the 100th day, up to the 1000th day, and so on. Because then you can look to see if they're approaching any numbers. Okay, and this is the idea that we have here. We are going to look at the partial series as a sequence. So in other words, we're going to look at S1. S1 is how much water you've added on the first day. S2 is how much water you've added in total up to the second day. S3 is how much water you've added up to the third day. And then you would look at like S100, how much water you've added up to the 100th day. You would look at S1000, how much water you've added up to the 1000th day, and so on. And so the partial series, in other words, those sums up to that particular day, we're going to use those to make a new sequence. And we want to see if this sequence converges to something. Because if you look at this, where should all these partial series be heading towards? If you keep on looking at like the sum of the first 100, the sum of the first 1,000, the sum of the first million, they should be getting closer and closer to the series that we're looking for, right? After you've added up the infinite number of terms. So this is a little confusing because there's several sequences here. There is the original sequence of ANs, which is how much water I'm adding. So I'm going to put OG sequence. And then you can look at the sequence of partial series. So this is the sequence of partial series. So if I just say the sequence, I mean the original sequence. If I'm talking about the sequence of partial series, I will say the sequence of partial series. Now this is weird because the sequence of partial series, you have to deal with an original sequence, right? So if you say sequence, it doesn't really specify which one you're talking about. Okay. So let's go through and let's calculate these. Okay, we're gonna use Wolfram to do this. Cool, cool, cool. So I'm gonna open up a Wolfram. Shit, where's my Wolfram? There it is. Okay, 1 second. Technical difficulties again. Okay, why am I not able to change the window? There we go. Okay. So, let's make a function for my AN. Okay, so what was my formula? It was 2 times 0.5, 1/2, right? To the power of n. Boom. Okay, now let's make another function which we'll call S n. And that's going to be, so Sn is the sum of the first n terms, right? So I'm going to use my sum command, and I'm going to tell it to sum the terms of my sequence. So does everyone see how I made a formula AN for my explicit formula for the sequence, and then I'm making a new, function called Sn. Sn is the sum of the first n terms. Or so I guess actually let's use a different variable here. Let's put sk. Does that make sense? So we'll do n will be the variable. We'll think of n as the variable we use for the sequence. We'll think of k as the variable we'll use for the partial series. Yeah. Okay. Now we have to tell it how much we're summing. We want k to go from 1 to k. Oh shit, is that even gonna work? Yeah. Okay, let's see if that works. So we want to do S of, just like plug in a random thing, let's see if it does it. S of 10, or 19. It doesn't want me to do that. Yeah, and 2 times point... Oh, it's to the n minus 1 power. Thank you so much. You're correct. It was to the n minus 1 power. That was a good catch. It's not 1/2 to the n, it's 1/2 to the n minus 1. Okay, I don't know if that's going to make a difference though. Okay, so I made a mistake there. Okay, I typed this in wrong. Okay, k will go from 1 to k. Why is it not letting me do that? Okay, let's look at the sum command. Maybe I'm just typing in the sum thing wrong. I want my variable to be k, so it should say k equals... Oh, I think I need it. Oh, okay, this is what I have to do. I'll put an I here. There we go. That's it. There we go, cool. Okay. So. Okay, I did it right. Sorry. I forgot. Okay, so when you do this, I guess I should point this out. The k here tells you how far the partial series is going, right? From 1 to whatever k is. You have to use a different variable name here. So, because my sum variable is I, my I is starting at 1, and then it's going to end at whatever the K was that you gave it. So you can't use the same variable. Like I can... because otherwise, if you use the same variable, it like plugs in the number at the bottom, and then it makes no sense. So you have to use separate variables there. Okay. So this is what we're going to look at. So, for instance, on the first day, you filled in 2 gallons of water, right? So S of 1 should be the 2 gallons that you put in. Boom. So do you see how S of 1 is 2? Let's see what S of 2 is going to be. So remember, on the first day, you put in 2 gallons of water. How much did you put in on the second day? 1 more gallon. So S2 should be the 2 plus the 1, correct? Boom, you get 3. So does it make sense? Like, it's actually doing it properly so far, right? I'm like just showing us that what we expected is happening. Okay, so what I want to do is I want to make a table of this. So I want a table of SI. Okay, so I'm going to give it a list of numbers to plug in. Let's have it start at... Oh, let's do the table command. I always forget how to type it in. So my variable is I, and how far should we go? We want it to plug in from 1 to what? Let's look at the first however many days. How many days should we look at? It's like someone throw out a number. Cool, 10 days. Sounds good. I always put 19. Okay, so on the first day you put in 2 gallons of the water. On the second day you put in a total of 3 gallons of water. On the third day you put in 3.5 gallons of water, and then 3.75, 3.875, 3.9375, 3.96875, 3.98, 3.99, 3.99609. Looking at this so far, in total, how many gallons of water does it look like you'll ever fill in? Just like looking at what we've got so far. My guess would be 4 in total. And we can like maybe go out to 100 days and see if it changes much. So you see how? Yeah, exactly. So what you notice is that the sequence of partial series appears to be converging to 4. And that's the idea here. If your sequence of partial series approaches a number, that's actually what the infinite sum or the original series is equal to. And I'm gonna write that down on our notes. But I wanted to show you that it actually makes sense with this particular example. You look for the first 100 days and you're like, look, those numbers are just getting closer and closer and closer to 4. And you can see Wolfram, it's set right now to only use up to 6 decimals. So do you see how once you get past 0.99999, it just starts rounding it to 4, because it's like, look, you're so close to 4, and it's called a fixed precision. I'm only going to be accurate up to 5 decimals. After that point, it just starts rounding to 4, because it's literally that close. Okay, so let's go back to the notes and write this down, because this is an important breakthrough for us. Sounds like we're in therapy or something. We've just had an important breakthrough. We figured out the source of our childhood trauma. Okay, so the value of the infinite series, or just series, is defined to be the limit of the sequence of partial series. So in other words, S, which is your sum of all the infinite number of terms, is defined to be the limit as k goes to infinity of sk, which is the same thing as the limit as k goes to infinity of the sigma k equals 1. Oh, sorry. n equals 1 to k of an. Okay, I'm going to put some boxes around things here so you can distinguish them. So here's our S, our infinite sum. And these are the, in green, the limit of the partial series. The limit of the sequence of partial series is in green. The value of the infinite series is in red. So we, instead of actually adding together an infinite number of terms, what we do is we say, okay, let's see what you would get if you add up the first k terms and then take the limit of that. It's like basically what we do in everything. And actually this should be sort of familiar. If you look at the limit of the partial series, what does that sort of look like here? The limit of the partial series, this stuff should remind you of something a little bit. It looks a lot like something we've dealt with a long time ago. The limit of a sum. Yes, yes. So you look at this and you're like, holy shit, this looks like a Riemann sum. Which means what's this gonna be connected to eventually? Well, what does the limit of a Riemann sum become for us? Yes. That's why we learn this with integrals, because we are taking the limit of a sum. That's the limit of a Riemann sum is a definite integral. So eventually we're going to figure out like, oh shit, like the way you solve this is with a definite integral. Does that make sense? Like you're supposed to like be thinking forward of like, what does this look like what does this look like that I've done before? Oh shit, it looks like all this other crap we've been doing. No wonder it's in this class after we've learned about integrals. Okay, now there's two things that might happen. If your limit exists, if the limit of the partial sequence exists, we say that the series converges. Remember how we were just talking about improper integrals? The improper integral will converge or diverge. I just talked about how this series is basically an integral. So if integrals can converge, then series converge. So if the limit exists, we say the series converges. If the limit doesn't exist, then we say that the series diverges. Which would mean like the sum goes to infinity or something like that. Sometimes an infinite number of terms will add up to infinity. But sometimes an infinite number of terms will actually converge to a particular value. Do you remember how for the improper integral, sometimes when we were integrating towards the asymptote, I was talking about as you go to the asymptote, it gets infinitely tall, but it still has a finite area? Same idea, basically. Okay,